Hello again, and welcome to our lecture on inverse trigonometric functions. I hope you've enjoyed the last few lectures developing trigonometry. You'll remember that we defined the trigonometric functions and we learned how to evaluate them for various angles, not only acute angles, but any angle, positive or negative. And then we had some fairly difficult lectures on graphing trigonometric functions. I'm the first to admit that's a non-trivial skill, but keep in mind the sine and cosine have that wave motion, and also keep in mind that unusual tangent graph. We'll be seeing it again today. Well, what about these inverse functions? You might recall a few lectures ago we developed the logarithmic function as the inverse of the exponential function. The exponential function was a rising exponential curve, and you remember it passed the horizontal line test. It was a one-to-one function, and hence it had an inverse. So we'd like to do the same for the trigonometric functions. We'd like to find their inverses. So think in your mind a moment, what do the graphs of the trigonometric functions look like? Here's sine, cosine, tangent, etc. And you might immediately say to yourself, it's not going to work. Why not? They aren't one-to-one. They don't pass the horizontal line test, do they? Horizontal lines can hit the graph of, say, the tangent function or the sine function more than once. In fact, infinitely often. So what do? How do we define these inverse trigonometric functions? Well, the key is to restrict the domain of the corresponding trigonometric function to a little piece of the graph. And on that piece, the function will be one-to-one. Okay, let's start by, say, looking at the most important inverse trigonometric function, the inverse sine function. How does it go? How do you develop the inverse sine function? Well, you start with f of x equals sine x, the graph of the sine function. And here's a picture of it. And again, it's not a one-to-one function. Horizontal lines can hit many, many times. But if I restrict the domain to the closed interval minus pi over 2 to pi over 2, on that little interval, you see that the function is one-to-one, and hence it has an inverse. And the inverse is called the inverse sine function, sometimes called arcsine. I prefer that word arcsine, but both are used interchangeably. So what would the definition of the arcsine function be? Well, the domain of the sine function, the restricted sine function, is minus pi over 2 to pi over 2. That will be the range of the arcsine. And the same way, the range of the sine function is minus 1 to 1, and it still is that range when I restrict the interval, and that will be the domain of the inverse sine function. So here's the formal definition of the inverse sine function, or arcsine. Y is arcsine x if and only if the following is true. Sine y equals x. Well, of course, that's always the definition of an inverse function. But you have these domain and range restrictions. The domain of arcsine is minus 1 to 1, and the range is minus pi over 2 to pi over 2. Again, why are these restrictions there? Well, remember, the range of the sine function was minus 1 to 1. That becomes the domain of its inverse. And in a similar fashion, the domain of the restricted sine function is minus pi over 2 to pi over 2, and hence that becomes the range of arcsine. Again, that notation is y equals arcsine x, or sometimes you'll see it written as sine inverse, a little minus 1 of x. Okay, on a calculator, I've looked at calculators, various brands. Some have arcsine on the key, and others have sine inverse. And in fact, the button for the inverse sine is usually right above the sine button. You'll see it right above. Keep in mind that arcsine is an angle, isn't it? Arcsine is an angle. It's the angle whose sine is x. Let's do some examples. Let's compute some inverse trig functions. Okay. This is fairly difficult sometimes because you have to backtrack to trig values in order to find the answer. For instance, what is arcsine of a half? What is arcsine of a half? Well, here's what we're really asking. Can you think of an angle whose sine is 1/2? Sine of something equals a half. Now, what angle has sine equal to a half? Pi over 6. The sine of pi over 6 is a half, so the inverse arcsine of a half is pi over 6. And notice that pi over 6 lies in the correct interval minus pi over 2 to pi over 2. So we say arcsine of a half is pi over 6, and you can check that with a graphing calculator. I did that with my calculator, and the answer it gave me was approximately 0.523599. Now, some people would recognize that as being a decimal approximation of pi over 6. I'm not sure I would, but that is a decimal approximation of the exact answer, pi over 6. Let me reiterate. Lots of angles satisfy the equation sine theta equals 1/2. Lots of them do. But in this restricted interval, minus pi over 2 to pi over 2, pi over 6 is the only value. Okay, because we have to make this function 1-to-1. Let me make one other comment about the notation. I said that you sometimes write sine with a little -1 of x. That's an unfortunate notation. The reason being, you might think that means 1 over sine x. But 1 over sine x is cosecant, isn't it? It's not the inverse sine. So again, I personally prefer the word arcsine over sine inverse. But again, both are acceptable. Let's do some more examples. What do you think the arcsine of 0 is? Well, go back to the sine function. Sine of somebody equals 0. Sine of 0 is 0, so arcsine of 0 is 0. How about arcsine of -1? What would the arcsine of -1 be? I need some angle whose sine is -1, and that angle has to be in the proper domain, that restricted domain. Minus pi over 2, right. Arcsine of -1 is minus pi over 2 because sine of minus pi over 2 is -1. You can see how this works. You have to really be good at trig values to be able to evaluate inverse trig values. Of course, there's some good news here. These are built into your calculator. Let's do another one. Trick question coming up. What's the arcsine of 2? The arcsine of 2. All right, let's think about it. I need some angle whose sine is 2. But wait a minute. The sine function is always in that sandwich between -1 and 1. It can never get up to 2. So it's undefined. Arcsine of 2 is undefined. On a calculator, when I punched in arcsine of 2, the calculator didn't break. It just gave me back a message saying non-real result, or non-real. Now, what does it mean here? Well, remember we talked about complex numbers a long time ago? Well, it turns out that arcsine of 2 actually has a value if you're allowed to use those complex numbers. But we aren't going to do that. So for us, arcsine of 2 is undefined. Let's graph the arcsine function. Now, here are some of the features to keep in mind. First of all, arcsine of 0 is 0, so it's going to pass through the origin. It goes through the point 0, 0. Now, the domain is -1 to 1, and the range is minus pi over 2 to pi over 2. Let's plot a couple of points, and I'm going to do it sort of backwards. I'm first going to figure out what the sine function gives, and then I'll translate it to arcsine. The sine of pi over 2 is 1. So on the graph of the sine function, pi over 2 comma 1 is on the graph. So for arcsine, 1 comma pi over 2 will be on the graph, and here you see it on the graph, 1 pi over 2. That's the high point of the arcsine graph. And then it passes through 0, and it's an odd function, just like sine is an odd function. So you get that bottom point at -1, minus pi over 2. So that graph is the mirror image of the sine curve restricted to its smaller domain. Isn't that interesting? It's kind of an interesting curve, I think. It's a little short thing because the corresponding sine curve was cut off between minus pi over 2 and pi over 2. All right, we've defined inverse sine. There are 5 more trigonometric functions. I'm not going to go through all of the definitions and play with all of them, but let me just point out some of the ideas of developing the other inverse trig functions. And in particular, later on, we'll see kind of a puzzle come up. Let's look at cosine. How could we define inverse cosine? All right, well, I've drawn a graph of the cosine function here, one of our old friends, up and down, up and down. It's not 1-to-1. We have to do some restrictions, don't we? What would be a good interval to select to make it 1-to-1? Well, how about 0 to pi? On that interval, and it's indicated in green on the graph, on that interval, indeed, the cosine graph passes the horizontal line test, doesn't it? It didn't pass it on the full range of its domain, on the full domain, but by restricting it, it's 1-to-1. So here is the definition of arc cosine. Y equals arc cosine x if and only if cosine y equals x, and here come the restrictions, x is between -1 and 1, and y is between 0 and pi. 0 and pi is, that's the restriction we made. The x part, -1 to 1, that's because it's still going between -1 and 1, like cosine always does. Here's a graph of arc cosine x, cosine inverse x. Notice some of the key points. You might remember that cosine of pi over 2 was 0. That means that arc cosine of 0 is pi over 2. You reverse the points when you do an inverse. You might remember also that cosine of 0 is 1. That means arc cosine of 1 is 0. And you see it there on the graph. Kind of a funny looking graph, isn't it? But that actually is the mirror image of our restricted cosine graph that we looked at a little bit earlier. Let's turn to tangent. This is perhaps my favorite inverse trig function. Here's a picture of tangent x. Tangent, you remember, has those repeated kind of curves there. It has those vertical asymptotes at pi over 2, 3 pi over 2, minus pi over 2, minus 3 pi over 2, etc. All right. First item. Is it 1-to-1? Not even close. Horizontal lines hit this curve infinitely often. Let's restrict the domain. Same pattern here over and over again. Let's restrict the domain. What would be a good domain? Well, I think everybody would vote for minus pi over 2 to pi over 2. And now that's an open interval, isn't it? Because minus pi over 2 and pi over 2 are not in the domain of tangent. But it'd be the open interval. That would be a good chunk to select. And on that open interval, tangent is indeed 1-to-1. Imagine just erasing the rest of the tangent graph and being left with that middle piece. So what's the definition of arctangent? Well, I think you know the game. Y is arctangent x if and only if tangent y equals x, and now we have to flip the domains and ranges. So let me think about it. The range of the tangent function is -infinity to infinity. So the domain of arctangent is -infinity to infinity. In a similar fashion, the domain of tangent was minus pi over 2 to pi over 2, the restricted domain, And hence, that will become the range of arctangent. Domain turns into range, range turns into domain. So there's the final definition of arctangent. Now, what do you think its graph's going to look like? What do you think the graph of arctangent is going to look like? Well, let's go back to tangent. And again, we're focusing on that single piece there in the middle. Notice it has two vertical asymptotes. Well, the inverse then will have two horizontal asymptotes, won't it? By symmetry. Isn't that interesting? So we'll have a couple of horizontal asymptotes here. And in fact, here's the graph of arctangent x. It's an odd function. It goes through the origin just like tangent did, and that's a mirror image of the tangent graph on its restricted domain. And notice those horizontal asymptotes at pi over 2 and minus pi over 2. Interesting, isn't it? Yeah. This graph, by the way, this function arctangent comes up all the time in calculus. It's amazing. It plays a big role in calculus. We can't see that yet in a pre-calculus course, but you have to trust me. Trust me. I'm not lying to you here. This function is a biggie for calculus. Okay, let's step back and do some computations. Make sure we're comfortable with these definition of inverse cosine, inverse tangent. What would the arc cosine of square root of 2 over 2 be? What do you think? Square root of 2 over 2. Well, we're asking the following question. Can you find an angle, some angle, whose cosine is square root of 2 over 2? Cosine equals square root of 2 over 2. Oh, pi over 4. Yeah, that's a 45-degree angle. That is arc cosine of square root of 2 over 2. How about arctangent of minus 1? Okay, I need some angle whose tangent is minus 1, and it's in the proper interval. And the answer, right, minus pi over 4, because tangent of minus pi over 4 is minus 1, and minus pi over 4 is in that restricted interval minus pi over 2 to pi over 2. You can check this on your calculator, and you'll get those answers. And you can also check it on the graphs. If you look at the pictures, you'll see that these answers make sense. All right, good going. I think we're pretty comfortable now. Not only calculating trig values, but reversing it and calculating inverse trig values. It's difficult. Success in calculating inverse functions requires a certain